Hi, welcome back. In this video, we're going to discuss about the estimation error. Okay, I hope you guys still remember that in my previous video, in the early part of my previous video, I explained to you the general form of the confidence interval to estimate population mean, okay, which is given by x bar minus e, that is the general formula to find the lower boundary, and x bar plus e, that is the general formula to find the upper boundary of the confidence interval. So here, E here is the estimation error. Okay, so let's talk more about this estimation error. Estimation error is also called a sampling error. So you see, a sample can never really ultimately represent the whole population. It can be a good representative of the whole population, but it can never really ultimately represent the whole population. So when you collect data from sample instead of the whole population, there will always be some likelihood of error. Okay, when you want to estimate parameter using sample data, so you are bound to make some error. So this is called the estimation error, the error that occur because you do sampling. Okay, so now let's recall our example 2.1. Okay, so in the previous example discussed, we obtained this confidence interval, a 99% confidence interval to estimate population mean of the weights of steel sheets. Remember? You still remember, right? Okay, so the confidence interval is given by these two values, okay? This is the lower boundary and this is the upper boundary. So if we compare and you get this value using this formula here, okay, x bar minus z sigma divided by square n, so that is your A, okay, the lower boundary, and then x bar plus z sigma over square n, so this is your B, the upper boundary. So let's compare this formula to the general formula, x bar minus E, x bar minus z sigma over square n. Alright, so can you see that the estimation error can be calculated? The estimation error formula is actually within the confidence interval formula presented to you in my previous video. So in this formula, the estimation error is actually this element in the confidence interval, okay, z alpha over 2 multiply sigma divided by square root n. So it's same for both sides, right? For the lower boundary and upper boundary, the estimation error is actually the same thing. Alright, so yeah, in this formula, this is the estimation error. Okay, so if you calculate this, so 2.5758 multiply 2.4 divided by square root 26, and you will get 1.2124. So this is the magnitude of error that we have, alright, when we try to estimate population mean using this confidence interval. This is the magnitude of the error, which is 1.2124 kilogram. Okay, so this is also equivalent to the width of the confidence interval divided by 2. Okay, so please remember this. Please remember this. Estimation error is also equivalent to width of the confidence interval divided by 2. And in this solution here, we can also see that the width of the confidence interval is given by the upper boundary minus the lower boundary, and you will get 2.4248 kilogram. And it is also equivalent to 2 estimation error. So you see here, estimation error and width are closely related, okay? So if the width of the confidence interval is bigger, then so is your estimation error. Does that make sense? Right? So if your width of confidence interval is small, and so does your estimation error. So ideally, if you want to do an analysis, if you want to estimate, okay, a parameter using interval estimate, okay, using confidence interval, then of course, ideally you would want to find a confidence interval that will give you smaller error. Am I right? Logic kan? So smaller error means better estimation. Okay, smaller width implies smaller error, thus you will have better estimation. So your analysis is better because the error is smaller. So let's take a look at the other formula to find estimation error. Okay, in the other two formulas of confidence interval. So this is what we did in exercise 2.1. For exercise 2. For the case of sigma square unknown, sample size greater than 30, the estimation error is this. Very similar to the first formula. The only difference is that here you use population standard deviation, and here you use here is sample standard deviation. Okay, and as for the third formula, the estimation error is this one. Okay, T alpha over 2 nu S divided by square root n. Okay, so these are the three estimation error formula. So if your confidence interval used this formula, so the estimation error is given by this formula. Okay, if your confidence interval is calculated using this formula, so the estimation error for the calculated confidence interval is this formula. Boleh ke? Kan? So let's talk about how to reduce your estimation error. Okay, how do we manipulate these formulas? Okay, how do we manipulate the elements in this formula to reduce the magnitude of your estimation error? Okay, so there are three ways that you can manipulate, all right, or that you can use, okay, to reduce your estimation error. Number one, okay, for example, let's consider this formula, okay, which is taken from the first formula here. Okay, so the sample size, if you have bigger sample size, larger sample size, it will result in smaller estimation error. So this is like mathematically, all right, if you look at this formula, if the denominator here is bigger, okay, if the denominator bigger, then it will give you a smaller e. Okay, so yeah, so if you want to have a smaller estimation error in your parameter estimate using confidence interval, then you should collect data from a large sample size. Macam tu lah, okay? So, increasing your sample size will give you better estimation. And then let's see what happened if the population standard deviation here increased. Okay, if a numerator increase, if the numerator here increases, okay, increase, if you have bigger numerator, then the overall calculation will be also bigger. Okay, so bigger population standard deviation will give you bigger E. Alright, so this is just mathematical logic. This is just mathematical logic. So meaning that if your data is widely spread, correct or not? Standard deviation is about spreadness of data, right? Consistency of data. So if your standard deviation is large, it means that your data is very spread. So a spread data will give you large estimation error. So this is another factor that will affect your estimation error value lah. Okay, so that's why we always say that consistent data is better. That's why we always say that consistent data is better, because it will give you better estimation. Your analysis will be more precise and accurate. So yeah, that is another thing that will affect your estimation error value. Okay, and lastly is the significance level. So if you still remember, significance level is given by the confidence level. For example, if your confidence level is 95%, so your significance level is 0.05. Okay, so same goes here. Okay, from the mathematical logic, all right, if your significance level increase, what will happen to this whole formula? Okay, this value will decrease. Okay, so in this case, increasing your significance level will reduce your estimation error, meaning that bigger significance level will give you better estimation, but yet again, you should not choose such a big significance level, then it will not actually give you good estimation also. So normally alpha 0.05 is ideal, alpha 0.1 is also ideal, but alpha greater than 0.1 doesn't really give you better estimation. So that is like more on the theoretical part, okay? But generally increasing sample size, reducing ataupun getting a more consistent data, and increasing the significance level will give you smaller estimation error, which means that you will get better estimation. Okay, so that is the concept about estimation error. Remember, smaller estimation error is better because it'll give you better estimation. Is that okay? Now, if there is any part of this explanation that you don't understand, do not hesitate to just PM me immediately right now. Okay or not? Now, next we're going to look at another example, okay? Another example that will use the third formula here. So I'm going to show you how to use this third formula. Okay, so stay tuned for the next video. Bye!